Okay, here we are, video 2 of chapter 8, lesson 1. And we're talking about observed minus expected. So the observed value is the y part of that dot, and the expected value is the y hat. So what we can say is the observed minus the expected is y minus y hat, because we're talking about vertical distance. The x is the same. I'm not worried about the x. It's for that particular x value of 1200 on the SAT score. So what we have here for the observed value, the actual value was 3.92. The expected value, what we got from the equation, was 3.21. And what this distance is, and that's the vertical distance, meaning straight up and down, is 0.71. That has a very specific name. And we're going to go back to the fathom here and look at it again. And hopefully all this is going to match right back up there. And it does. All right, so that distance right there break out the pen, is 0.71. That is called the residual. So let's write it over here on this. This is the residual. Residual is really important to us. And the variable that we use to represent residual is the letter E. Not as in like the natural logarithm, as in E. And why is it E? No! It's not because it's the second letter in residual, because we can't use the first one of R, because R is the correlation coefficient. Nice try and thinking that it was R. R is the correlation coefficient. It's E, and not because it's the second letter. It's E because E is for error. Thank you. Today's episode is brought to you by the letter E and apparently the number 0.71. It is E for error. Very, very, very important that we keep that in mind, because really as we look back at what this is our inability to correctly predict the true value. And our residual or our error in our model is 0.71. Now keep in mind that what we're looking at here is we have a value that the observed value is above the predicted value. That means that when we do y hat, or I should say when we do when we come back here, you pen, when we do y minus y hat, if the observed value is larger than the predicted value, you're going to end up with a positive residual, as we did here, 0.71. But I could also end up having an observed value in this situation that is below the predicted value. So it's below the line of best fit. And as I do a subtraction here, I'm subtracting, because it's below, a smaller value from a larger value, which means here I'm going to have a negative residual. So I can look at this and say, oh, look, if my value is below the line of best fit, if my observed value is below the line of best fit, observed below the expected, I'm going to have a negative residual. However, if I have an observed value above the line of best fit, I'm going to have a positive residual. Consequently, I can work the other way. I can say, hey, look, I've got a negative residual. Therefore, that tells me that if I've got a negative residual, that the observed value is going to be below the line of best fit. And if I've got a positive residual, the observed value is going to be above the line of best fit. So, keeping that in mind, let's leave this for a second here and come back to these pages right here. Now, here's what we had. We had that y hat is 3.21 for our x value, our SAT score of 1200. So on the line of best fit, with an SAT score of 1200, we had a predicted freshman year GPA of 3.21. Now, what if we actually had a different data set, okay, or we had another piece of data in here, and what the observed value was? I gave you this information, I said, well, you know what? The residual for that piece of data is, let's make it 0.25. So, can you tell me what the actual score was for the freshman year GPA? And the answer is, well, of course I can. Because here I know that the residual is 0.25. So the first thing I need to think is, does that mean that the observed value is going to be above or below the line of best fit. Since my residual is positive, that means that the observed value is going to be above the line of best fit. How far above the line of best fit? 0.25. So what I can do is I can take that original value, my predicted value of 3.21, add 0.25 to it, and I would expect to find that the observed value is going to be at 3.46. I'm hoping that that is something that works well for us. Okay. So, why is it called the least squares line? Well, let's take a look at Fathom again here. Now, think about what happens here as I draw on this again, okay? Here's the residual for this value right here, and this value is where the SAT score was 1200, and here's the SAT score. It might be 1000, I don't know exactly. I could look, but I'm not that curious. But what's going to happen if I take all of these residuals and I add them together? What is that going to do? Well, it turns out that if I take all those residuals and I add them together, they're going to be 0. Which means that that's fine, but I don't get to do much with residuals. Just like when we're talking about standard deviation. If I took all the distances from the mean and I combined them, I would get 0. So to eliminate that issue, what we did when we were working with standard deviation, we took each value minus the mean and we squared them. And that's what we're going to do here, is we're going to take each of those residuals and we're going to square them. And that's why this is called the least squares line, because it is the square of the residuals. So what I can do is I can bring this up and it's going to show me the squares. Here we are. Here's the actual residual. But what this square represents that distance as a square, meaning residual squared, 0.71 times 0.71. That's a square. And all of these are squares. Well, fire alarm's going off. That's good to know.